Okay, so I copied that data and I'm going to paste it in here. So first thing I want to do is I just want to, if I didn't, you can either graph it by hand, which is fine. I'll recommend that. On the project we're about to start today, you're going to do both by hand and computer graphs. Since I have the computer here, I'm going to just ask for a chart. And then I would prefer a scatter plot. Come on, scroll down. There you go. So I can see the world records dropping over time. Now, can it drop forever? The answer is no, it can't drop forever. Eventually, we're going to reach a kind of a peak as to how fast a person can run. Once I get that, I go to Customize, Series, and then I want to see a trend line. And there's almost exact same procedure for doing this in Excel. And then I want to show the label as an equation. And close it. So here, I get a little tiny number in scientific notation, which we talked about a long time ago. So I'll have to figure out what the heck that means. So I need a screenshot of that. There we go. I'm just going to grab this whole thing. Okay, so next thing I need to double check is, did I follow the directions? Because I have a problem with reading directions. Anybody else have a problem with that here? Okay, good, not the only one. All right, directions said, where'd you go? Here you are. Let the horizontal axis represent the years T, where T is the number after 1990. Ooh, is that what I told the graph to do? No, I plugged in the actual year. And, oh, I read that wrong, 1900. Okay, so I got to redo my graph because I didn't read the directions. So how am I going to fix this? Oops. To do 6, we have to do 5 first because we got to come up with a model. We have to come up with an equation for a line. And the problem is I plugged in the year. Do you think that's what you did maybe, Colt? Yeah, so what I'm going to do is I'm just going to sneak a new column in here. So let's get my menus, insert a column to the left, and I need a new column called years after 1900. So then this year will be 12, and this will be 21, and that will be 30, 36, 56, 60, 68, 99, 108, and 109. Cool thing is, because the way I made the chart, it tried to redraw. Ooh, and I messed it up. Check that out. All right, so I think I'll delete that chart, try again. So I'll try again, highlighting these 2 columns, make my chart. And so I'll show how to do it without the computer too. So let's see, chart and scatter. And okay, so there's my same data dropping. I just changed the scale at the bottom, right? Not a big deal, but it'll give us a better y-intercept. So let's see, series, trend line, label, equation. Now at the moment there's no labels. I'll go back and put those in later so we can just get to work. All right, does my slope look like it changed, or does it look like it's the same? Yeah, I don't think it did actually, because all I did is shift the data. I didn't change the angle of it. Notice the line, notice the points have the same shape they did before. Yeah, and the slope shows the shape of the points. Okay.
Like the diameter of the circle, or like?
No, the way they drop here, the angle they drop at, that's not going to change when I change whether I do the year 1908 or I call it 8. Okay, because then all the points are the same distance apart horizontally. Okay. So it still has the same slope, but changes the y-intercept. So what does this tell me here? That tells me if I plug in 0 for x. What is x in this situation? Years since 1900, so that would be 1900. So in 1900, the time it took to run this race should have been around 10 seconds. 10.6 seconds is what that tells me right there. And the slope tells me how it changes per year. So it's dropping by a certain amount of seconds per year. So we're going to expand that out and see what it means. All right, so let me copy this. Zoom out just a little bit. So that's, and let's see, look at same shape right there versus right there. Just different numbers on the axis. So bye to that, recopy. Here we go. All right. So what does this mean here? Anybody remember what that big E means from way, way back when we dealt with big and small numbers back in chapter 1? It's an exponent, yeah. What's the base of the exponent? 10. This is a computer's version of scientific notation. So this part right here means negative 8.71. That big E means times 10, and whatever comes next has to be the power. So that's a negative 3. What do I do with 10 to the negative third? Anybody recall that part from last term? It's a good review. What does it mean? What do I do? What's that? Yeah, it's decimal places, yeah. So if it was 10 to the positive 3, that would make the number bigger, moving the decimal to the right. This is 10 to the negative 3, which is going to make it smaller, moving the decimal to the left. How many places do I get to move the decimal? 3 times, yeah. So I have to go hop 1, 2, 3 times and have a new decimal. So that means I'm going to have a 0.00871, and it's a negative number. So that's the real number version of the slope. So here's what my model looks like. Let's see, what did they say to use for variables here? They said to use R for the record and T for the time. So it looks like I get a slope of negative 0.00871 times the years after, that's T, plus 10.6, I think was our starting point there. So double check on that model. Yeah, there's my y-intercept, and this is my slope right here. Okay, before I hit continue, can somebody help me out? So let's see. This axis right here is T, and that's, again, years after 1900. And this is R, and that's the world record in seconds. Which is time for the 100-meter dash. So what is a slope? Remember, slope is rise over run of negative 0.00871 mean. What are the units on that slope? What's the units for the rise? Well, that's the number, right? What's the units, though? What am I measuring? 10 what? 10.25 what? 10.5. Yeah, those are the time it took to run the race. That's seconds. Okay, so this is a number of seconds. And what's the run? What's changing over this direction? Years. So that's seconds per year. So here's what I want you to do right now. Write down a sentence describing this number right here, including referencing that negative sign, seconds, and years. What does all that mean in English? Give it a shot. Don't worry about being wrong. Write something down on paper. If you don't get any paper, type it up on your computer then. Put it somewhere. I need everyone to come up with a sentence. What do you think the slope means? World record time in seconds, changing over the given years. Write something down. Emily, you awake there? Oh, good. Write something down. Write something down. Okay. And often in problems like this, the slope is the most important number. doing, Emily? Ready to write? Paper? Write a sentence. You already wrote one? Oh my gosh, you're so fast. Sorry. Didn't mean to give you a hard time there. Were you at Annie late last night?
Yes, I was.
Okay.
We did until like 9:30, and then I still had to drive home.
Yeah. When does that start playing?
22nd.
22nd. Okay, so you got a couple more weeks of rehearsals, and then off you go. I think that's going to be hard to get tickets for because there's so many people in it. Like everyone they know is going to go see it. It's a big production. Okay, so I'm going to write down my sentence, and then you can compare yours to mine and see what you think. Uh-oh. That magic pen died. Let's try this. All right, so my slope again, m negative 0.00871. So the time to run a 100-meter race is decreasing by about 0.00871 seconds each year.
I said drop.
Since, what's that?
I said drop instead of decrease.
Yeah, drop is fine. Yeah, anything like that since 1900. And I probably should put the world record time. World record should be in there. So I just want to write a sentence that describes what that number means, right? So again, I'm focusing on the writing principle to try and be complete, but not too wordy. What were you going to say, Emily?
I'm not sure. That's what I was thinking was like, I was trying to put like the amount of time that it takes them to run, like they're running faster.
Yeah, that definitely means they're running faster, right? So that could be in the sentence too. That makes it a little more complete. Yeah. But in terms of the most important thing is using that number right there, right? And
Yeah.
we're measuring the amount of seconds it takes to run the race, and we're checking it every year. So I have to refer to both seconds and years because that's the numerator and the denominator for that number right there. And so it was a negative, so I also have to have decreasing in there.
Can you put the negative with?
Not if I say decreasing, I don't need it. So instead of, you could say changing by negative 0.008 seconds, that would be okay. But like if I said that to my mom, she'd say, what do you mean changing by negative? Like what would your mom say? She'd say the same thing. Yeah, so she'd want to hear drop this many seconds or decrease this many seconds. So often when I'm writing this kind of stuff, I think about my mom. Because she's not very mathy or scientific. My dad, on the other hand, is. And so I also think about him because he'd be way more critical. My mom would say, I don't get that part. My stepdad would say, what do you really mean? What do you mean every year? Forever? Since when? He'd be more critical. So that's my attempt at the sentence. And there'll definitely be a couple of questions because pretty much all this module we've been dealing with lines and slope. So there'll be a couple of questions saying, hey, what does the slope mean here? And I just need a sentence that says, based on the numerator, based on the denominator. So for me to write that kind of sentence, what I have to do is I have to write out, okay, what's my rise, what's my run, then I write the number, and then I write what are the units of the numerator, what are the units of the denominator. Once I have all that down, I can wrap my mind around the sentence. But until I write all that down, I don't got it. So it takes me a minute to think it through about what it means. What's that?
The slope is already equal negative 0.00871.
Well, so remember, let's see, new page. So we've got this standard idea of a line, y equals m times x plus b. In this case, we're replacing y with an r for the world record time, and replacing x with the time t. But we still have some number multiplied by t, and we still have some number over here. So for us, filling in this number and this number, we think our equation we think our equation looks more like this. So our m, we believe, is negative 0.00871. Actually, I'm going to change colors here. Let's make that R black. We'll make the T black. And then we'll switch back to blue for the B. I think that was 10.6. So when I look at something like this, to identify the slope, it's just that number in front of the variable. So the slope here is just the number negative 0.00871. Since it's a slope, what I usually do next is, if it's not already a fraction, I just throw it over 1 so I can show a rise and run.
And it's the 10.6 because that's started.
The 10.6 is the vertical intercept. That's the starting point. So the starting point for us would mean, well, what does 0 mean in this case for t? Since t is years after 1900, that would mean in 1900, that must have been the world record according to our model.
Well, it was 19.
Okay, but what did we define t to be, though? That's the question. It's not where the data starts. So we were told right here that t is the number of years after 1900. So t equals 0 would mean 0 years after 1900, so it would be 1900. So I could add to this table before 1912, I could throw a 1910 and put 10.6 in there. Okay, now it happens to be the same number as this one right here. No big whoop. That's okay. Go back to my notes here again. So this is what I believe the slope to be. What is r, the number over here, the y, that always talks about the numerator. What's r measured in? Seconds. So this number has to be some number of seconds. And the denominator is always related to the number over here. What's that measured in? Years. Right, so I'm just repeating how I think about how to interpret the slope to somebody. So this tells me it's a drop of this many seconds every 1 year. That's what it tells me. Okay. All right, we're going to do this one more time. But this time we're not going to use the computer to generate the model. We're going to calculate it ourselves. So here's my picture. So if you were going to draw your own line, which 2 points might you pick to use to make a line?
The ones with the line.
Yeah, this line is kind of guiding us toward it, so I'm pretty tempted to pick that point right there. And what other one maybe? I'm thinking either this one right there or that one right there. Which one do you want to go for? This one right here? Okay, so let's see. This is the second point in the list. 1, 2, 3, 4, 5. That's the 5th point in the list. So we'll look back at the list and get the 2nd and 5th point and try to find our own line. So you guys can help me out with this. I need a screenshot of the data.
Hey, giving you the table to the Y2.
Yeah, that's what we're going to do right now. Yeah, so the actual instructions for this were to plot these points on a piece of paper, take a straight edge, draw a line through them, and then try to find the equation of your line. And we're kind of doing that. We're saying that we're going to grab this point right here, and then what did I say? 1, 2, 3, 4, 5, 1956, that point right there. We're going to find a line through those 2 points. So start working on that. Find the slope first, then we'll talk about the y-intercept. Question? Okay. Oh, you don't get to measure springs today. We might do more of it on tomorrow. Wednesday? Yeah. So on the website, on the page for the lesson, there's a link to a video about measuring springs, and there's a link to a game for measuring springs. So take a look at both of those tonight. All right, so let's, what do I get for a slope? 10.1 minus 10.4. That's that change right there. And then the bottom, I
35.
get, is that 35 years? All right, so that's going to give me negative 0.3 over 35. What's that come up to be about? About 3 decimal places.
0.5.
What's that?
1.5.
At least more than that. Let's see.
We've got negative 0.0085.
0085. Okay. Let's go. Let's see. 4 decimal places maybe. So 008. Let's call it 0086.
Cool.
0086. That's not too far off what the computer said for a slope, and that's okay. So that's what we think the slope is. So next we have to identify a y-intercept. And there's a couple of ways we can do that. So I'm going to do it by just considering, set my board here, the tape is slipping. So consider, oops, whoa, how did I do that? Apparently I hit the wrong setting. Undo. Lighten up there, blue. Okay. So consider the equation y equals mx plus b. So we've just calculated, we think we know what m is right now, but we don't know b. So one way to do this is just to pick one of these points to plug in for y and x. Now before we do that, we got to make a slight modification to our table. And I rush into these problems sometimes without thinking it through enough. I was asked to make a variable called t that's years after 1900. So that means instead of using the number 1912, I should really be using what number? 12, yeah. So I need to reconsider that. And here I really need to be using the number 21. Here I need to be using the number 56, and so on. And that's going to matter. It's not going to matter for the slope because we subtract out the 1900 part, but it's going to matter for b. And so for my points, I need 21 for t and I need 56 for t. So which point do you want to pick to find b? The first point or the second point? First one? Okay. So that means I'm going to plug in 21 for my x. M, we just calculated, that's the negative 0.0086. And then if t is 21, what does y have to be here?
10.
That's going to be the 10.4. And then we can solve this for b. So on my calculator, I got to figure out what is negative 0.0086 times 21. Anybody got a number for me there?
Negative 0.1806.
6. On the other side, I have that 10.4. So then I have to add this number to the other side. And so I think that's going to give me 10.5806 when I add that over, which is pretty close to what number we found before. 10.6, yeah, it's pretty close to 10.6. We're getting a pretty similar model.
I got the next one too.
You got it now?
Yeah. I got it.
Okay, cool, yeah. It was just that first part. I think this was the part here that was.
Yeah.
I do that all the time too.
Thank you.
All right, yeah, I'll see you later. So it shouldn't be too much of a surprise that we got almost the same slope as in the model and almost the same y-intercept because we picked 2 points that we thought were pretty close to on that line. So we got close to what the computer said. So here's what we think our model is. The world record can be calculated, or we can predict the world record by taking negative 0.0086 times the number of years after 1900, and then add on to that, how many decimal places should we give this? Probably 2, 3. So usually the way I do it is I look at the data, and I usually go one more decimal place than the data shows. So 2 is usually what I would do. That's a problem here, because then my slope isn't good enough. But for the y-intercept, I'm just going to call it 10.58. So I would say 10.58. So this is another model. And depending on which points you pick, you'll have a slight variation on this. Like we played around yesterday, we had slight variations on that.
I got 9. It would fall below 9 seconds.
What's that?
It said to figure on the, it says to figure out what year the record will fall below 9 seconds.
Yeah.
So you would set R equal to 8.9.
You could set it to 8.9, or you could set it to 9, and you just want to be below that. So let's think about that for a minute. So you bring up that question. It's not this one. Let's go with number 6, right? Yeah. Use your model you created to predict when the world record would fall below. Yeah, so you could either set your model equal to something just below 9, like 8.9, or you could set it to 9 and then just pick a year after that. So there's a couple of different procedures. So we want to know when the record is going to be less than 9 seconds. The record can be calculated by using that. So basically, I want to solve the inequality, negative 0.0086 times t plus 10.58. I want that to be less than 9. Remember we solved inequalities last term? Almost the same as solving an equation. First step here would be to subtract the 10.58 from each side. That's going to give me negative 0.0086. Oops, t. It's got to be less than negative 1.58. All right. Now here's a trick. What happens when you divide by a negative number in an inequality?
You're supposed to flip the sign.
Yeah, you got it. So nice to hear your voice, Daisy. Thank you. So that means I have to now say that t has to be greater than whatever that is. So whip out a calculator, what is that? That's 1.58 divided by 0.086. Yeah.
18.3.
18.3? That would be bigger than that. Anyone else get that?
183.72.
183.72. So you must have missed a decimal somewhere.
Probably.
So 183.72. Anybody else get that? And you had the same numbers with a decimal in the wrong spot, right?
Maybe.
Yeah, you had 18. I think you said 18.37.
Yeah.
Yeah. So you just missed a 0 or a decimal point somewhere there. Yeah. So that basically what is t again?
Time.
Years after 1900. So 183 years after 1900 will be when? 183 years after 1900.
It'll be less than.
It'll be 2083 in a little bit. 183 years later. Yeah, so somewhere in 2018 right now, if the world record keeps dropping like this, then in like 2084, we would expect the world record to be around 9 seconds. If we do that right. What's that?
I can do that.
Yeah. I'm not a very fast runner. I can run for a long distance though. I have endurance, not speed. All right. So the model predicts the world record will fall in 2000. I'm going to say 84 because we have to be bigger than that number. Let's see if I got it right. Woohoo, I got it right. Nice. Okay. So that was exciting. Next. We're going to check out this video here.
So here we have a hanger attached to the end of a long spring. If we add a 50-gram mass to the hanger, it pulls down the spring to about, let's see, 25.8 centimeters. Now, if we add a second 50-gram mass, it pulls down the spring to about 21 centimeters. And if we add a third 50-gram mass, it's going to pull down the spring to, let's see, about 16.2 centimeters. So now we're going to take off those weights and add on a mystery block of wood. And it pulls down the spring to about 24.5 centimeters.
Okay, so the point of this is humans have been messing with springs for a long time, since after we started playing with metal. And it turns out that a spring will stretch when you apply a force to it. Weight is a force. Gravity is pulling down on some object. Now, if you pull the spring too far, you'll bend the metal beyond repair and it'll stop working as a spring anymore, right? If you don't put enough weight on it, you won't notice a difference. So there's masses that are going to be weights that are going to be too small for the spring and weights that are going to be too large. And let me see, Daisy, I need to switch so you can see me. Forgot about that. How do I do that? Right there. Hello. Okay, so I have a spring right here. Okay. So I got a couple of different springs we're going to play with. And Daisy, you're going to be my partner. You're going to help me. You're going to watch me try to stretch the spring with a weight. And then we're going to try and measure how far the spring moved for each weight. So it turned out that there's a couple people that discovered this, but it's attributed to a guy named Hooke, who was alive in the 1700s, maybe early 1800s, that the distance that the spring stretches is proportional to the amount of weight that's on the spring. So if you put twice as much weight on the spring, it'll stretch twice as far as it did before. Okay? Which basically is going to make a straight line if we compare the weight to the distance the string stretched. So we have to measure where the spring is before it starts stretching, make a note of the weight, and then how far it stretched with that weight. And what we're going to do is we're just going to put a bunch of different weights. So like here, I have a 0.5 kilogram weight, and we'll see how far the string stretches with 0.5 kilogram. I have a 200 gram weight. There's 1,000 grams in a kilogram. So we'll see how far a 200 gram weight stretches it. Not very far, right? Just a few centimeters. I also have a weight that's a whole kilogram, and we'll whip out a measuring stick. That one's a lot heavier, and see how far the whole kilogram stretches it. And I'm pretty sure it's not going to damage my spring, but I'm not positive. I seem to go back to where it was before. All right. And then I have a smaller spring. And the difference between these two springs, when you feel this one, you can feel it pulls easier. And the little spring, remarkably, is made out of slightly different steel. It's a lot harder to pull. Okay, so even though it looks like, hey, this is the wimpy spring, this is the tough spring, they're different metal, and so they pull different. And the diameter has something to do with that too. All right. And so we're going to do 2 different springs to just play around with. All right, so we're not going to finish this today. We're going to have to do a little measurement today and do some more tomorrow. Our goal is to then put a mystery weight on here, something we don't know the weight of, and see if we can notice how far it pulls the spring and use our data to predict its weight. So just like we used our model to predict when the world record was going to be at 9 seconds or less. Okay? We should be able to use a model for our data to predict, and that's how a lot of scales work. A lot of scales just have springs inside them. You know the scales with the dials on them? Yeah, the spring moves the gear moves the dial and tells us how much we weigh. Okay. Newer scales use a digital version of that, but it's a similar idea. All right, so we're going to repeat this, and I'd like you to try this for homework, and we'll do it in class. On the lesson 3.6, there's a spring scale app that you can bring up where you have these virtual springs here. And depending on your computer, some browsers, because this is like a video game, will try to prevent it from running. And so you might have to click on some warnings to say, please run it anyway. The spring is kind of controlled by 2 things. How much friction is going on in the pulling on the spring and how stiff the metal is. in the spring. And so you could change the kind of spring you're working with by just moving these sliders, increasing the friction, increasing the hardness, or decreasing the hardness will give you different change on the spring. And then you've got a ruler here that you can move around and measure. And so the goal is to see how far the spring stretches with each of these weights. Write it down. Oops, get off there. So you want a table of like 5 different points. And then once you get that table, you're going to make a line out of it. Once you have that line, you can then take one of these mystery weights, and based on how far it stretches, you can predict how heavy the weight was. Okay, so that's going to be our goal tomorrow. For today, we're just going to play around with measuring a little bit. So I'm going to get some tape measures out. Why don't the 3 of you get together and do some measurements, and then Daisy, you and I. Oh, Daisy, I forgot to switch screens again. You got to yell at me when I do that. Let's see. Hopefully I don't remember to switch back. Share. Okay, so I was demonstrating this app, which I got from the Spring Scale app on the 3-6 lesson, where you can stick weights on it. And it's kind of realistic. All right, stop it. With sound effects. All right, so, hey.
Hello.
Oh, okay. So we have a slight change of plans. We're going to start measuring stuff tomorrow because we have a special guest in here today. So I'm going to shut up for a moment and let them take over. So let's see. We have one online student. So if you want to come in front of the camera.
Perfect.
That would be
Hello.
fantastic.
Hi guys. So my name is April Torres and I'm the Trio Success Coach here on campus in Moore Hall.
And I'm Annie Smith. I'm a success coach and the Native American liaison.
And so the reason why we're here is because this is Success Week. And so we wanted to just introduce ourselves and let you know that we are located in Morrow Hall in the Student Success Center. And we wanted to remind students to meet with their faculty advisors now to get cleared for registration, as well as pick out your classes for spring term. You definitely don't want to wait until the last minute to do that because classes fill up quick, and most faculty members, as it gets closer to finals week, are very busy. So we want to respect their time as much as they would like to respect yours in helping you decide what your next steps are for spring term. So we also wanted to tell you about what we offer over in Morrow Hall in the Student Success Center. So we've got computers, printers, tutors, and workspaces, and you can ask success coaches about careers, degree options, transferring, degree audits, and anything that has to do with moving on in your future. And then success coaches can also help you find new study strategies, test taking, and test anxiety methods and ways to overcome those things, and how to juggle your life and college demands. So we've got a scavenger hunt here that Annie's going to pass out to you. And if you online would like this scavenger hunt, you can participate too. Just email your success coach and we can get you a copy. So the point of this scavenger hunt is to kind of get students more involved on campus, knowing where all the resources are. So if you follow the prompts on the scavenger hunt and you go to each department, get the answer to the question, and then turn it into the Success Center, Stephanie Brown will take those, and you'll get like a participation prize, but then it goes into a drawing for an even bigger prize. So, and I'm not sure exactly what that is. I hear it's pretty cool. Maybe. Don't quote me. So if you guys have any questions, don't know who your success coach is or who your faculty advisor is, you can come on over to Morrow Hall and find one of us, and we can definitely look that information up for you, even show you how to set up an appointment through Appointment Manager. But that's kind of how they want us to have you guys setting up appointments with your faculty advisors, is through Appointment Manager. Okay. Thank you so much for giving us a couple minutes.
Yeah, you're welcome.
All right. Bye, guys.
All right. So if you guys haven't used the Appointment Manager, you can get to that from the students page on the BMCC website, and most advisors put their notes in there. So that's it for fun with math today. We only have 5 minutes left, so we might as well stop here. Tomorrow we will measure stuff. So in the meantime, finish that homework for 3-5. We're going to find some lines tomorrow, and the prep for 3.6 is more about finding equations for lines and getting slopes. Have a good day.